where the function is x plus 3. Okay, let me look at the chat. But Mia is saying you're subtracting the value inside the square root from 3. Minus 3 doesn't make sense. Why minus 3? Oh, okay. No, it's written this way. So square root. So we're trying to find the square root of 3.98. I think this is a better way to explain it. Because the function is the square root of x plus 3. Okay. In this case, what's our x? Our x is 0.98. So we're treating this as the square root of x plus 3. X plus 3. So 0.98 plus 3. And then we approximate this. So the x is 0.98. So 704 plus 0.98 divided by 4, which is this, approximately 1.995, which is very close to, right, but not 2. So this is a linear approximation of square root of 3.98. All right, so this 0.98 comes back from the function. Because it's square root of x plus 3. So x plus 3, 0.98 plus 3, that's 3.98. For square root of 4.05, we do the same, right? That's square root of 3 plus 1.05. So x is 1.05. 704 plus 1.05 divided by 4, which is about 2, a little bit bigger than 2, but very, very close to 2. So this is a typical example of why we use approximation. Because the square root, like a square root of 2, square root of 3, square root of 6, square root of 7, and we have no idea about this irrational family, right? So all we do is we can approximate. We won't be able to get the exact value. That's why we call irrational, because it really does not make sense to human brain yet. So it's irrational family. So we want to approximate irrational numbers. So the calculator does exactly this. But this is just a lower level approximation, very rough approximation. If we want to be more exact, later on we'll learn quadratic approximations. So we go further. So we add to this. We will say, okay, add quadratic one, f double prime of a, then times x minus a squared. So that would be a quadratic, so second degree of approximation. And if we want to be more accurate, we will keep adding f triple prime, evaluate at a, then the difference being cubed, so on and so forth. All right. So the better calculator we buy, better approximation we will have, and the higher degree of derivative will go. Okay, that's one example. Any questions? For this one, so Amir is asking, what decimal places do we need to round from? Yeah, to make sense for this, you see, they round up to 3, right? 995, 0.995, 0.012, or maybe this can be rounded as 2.013. I would say 3 decimal places. Okay, so this question is saying, for what value of x is the linear approximation accurate to within 0.5? Or maybe what we want to do, we think 0.1. So we just, we're just trying to find the difference f of x with of L of x. Try to remember, so this is our f of x. This is our L of x. So this is a linear approximation. So we want the absolute value. Accuracy is in between negative 0.5 and 0.5. Well, we could add those two. We could rewrite this one as this. Okay, let's see example 3. The radius of a sphere was measured and found to be 21 cm with a possible error in measurement at most 0.05 centimeters. What is the maximum error in using this value of radius to compute the volume of the sphere? So we want to use the idea of approximation. It's allowed within certain error range. So let's use R to represent the radius of the sphere and the volume of V. So we know sphere has a volume formula 4/3 pi r cubed. And we make the measure, we denote the error in the measure the value by dr or delta r, right? This is the allowed mistake. Then the corresponding error in this calculated value of v, v prime or dv dr, right? You can call this just another notation, which can be approximated by the differential. Right? Differential is another name of the derivative of the function. So we can write dv equals to the 4 pi r squared dr, right? Related rates, just in this way we write as related rates, or we can divide it by dr on both sides. We can think as related rates. Or we can divide by dr on both sides. Then we still have dv over dr equals to 4 pi r squared. Right? In that case, we're treating v as a function of r. But we can write this way, right? Multiply by dr on both sides. We have dv equals to 4 pi r squared dr. Let me write this one. Remember, if we take dv dr, that will be 4 pi r squared. We can multiply dr on both sides. So we can write dv equals to 4 pi r squared dr. So we can write dr on this side. Right, write dr on this side. So dv, we just plug in all the value given. So dv, the differential of the volume is about 277. The differential, the error, right? We said, okay, let's this representing the error dv, right? So the maximum error calculated in the volume is about this much. This is how we use it. Approximation, the differential in applications. Okay, let's go back to linear approximation. Linear approximation is all about to find the derivative at the next point. But think about square root of 4. Right? 4 would be a very nice point because we know exactly what the square root of 4 is, which is a 2. So a usually represents, makes the function a very nice value. We know exactly what's going on. And we want to use the nice value to approximate the points around it. So remember this example, rational numbers for approximating irrational numbers. So let me do one because the example is not much. Let me try 4. So let's try together 4, all right? So 4, we want to find a linear approximation of L of x of the function at a. Right, so a is 16. And f of a, so this is for 4. F of a is f of 16. Now we can get a very nice value. So it's a 16 raised by 3 over 4. The 16 we can write as 2 raised by 4, right? Then multiply by 3 over 4. That becomes 4 times 3 over 4, that becomes 2 raised by 3. That becomes 8. Okay, so f of a, f of 16 equals to 16 with exponents 3 over 4. So we're writing 16 as a 2 raised by 4. Then 4 times 3 over 4, that becomes 3. So it becomes 2 cubed. 2 cubed is 8. So f of a is a very nice number. And we want to use this value to approximate the points around it. Think about a might be 15, right? Or maybe 15.99, or maybe 16.01, so on and so forth. We want to use this nice point to approximate the points very close to it. So we need to find the derivative of this function, right? Let's find f prime of x. So first we find the function value at a, then we need to find the derivative f prime of x. Our goal is to find f prime of a, but let's find the derivative of the function first. So 3 over 4 x raised by negative, 3 over 4 minus 1, negative 1 over 4. Then let's find f prime of a. So that's our derivative of the function, right? 3 over 4 power rule, 3 over 4 x raised by 3 over 4 minus 1, which is negative 1/4. Then f prime of a, which equals f prime of 16, which equals to, let me change the line, which equals to 3 over 4 times 16 over negative 1/4. So again, we rewrite 16 as 2 raised by 4. So 3 over 4, 2 raised by 4, then raised by negative 1/4. So that's a 3 over 4 times 2. So 4 times quarter, that's 1. 2 raised by negative 1. Okay, I'm missing equal sign. Equals to 3 over 4 times 2 raised by negative 1. That is a 3 over 4 equals to 3 over 4 times half. Right? 2 over 2 with exponent negative 1, that's half. So that equals to 3 over 8. So first we find f of a, which is f of 16. Then we find the derivative. So f prime of 16. So we need to find f prime of a, right? So we need to find f of a, we need to find f prime of a. So take the derivative of the function, then plug in 16. Now with those two values, we can write out our linear approximation. So we write out as L of x equals to the function value f of a equals to 8 plus the derivative, which is 3 over 8, times the difference, which is x. X means any point around 16. Any point around 16. Minus 8. Well, what's 8? 16. So that's it. That's the linear approximation That's the linear approximation L of x for this function at the point 16. All right, when x equals to 16. When x equals to 16. Even this is the a here, a equals 16. A is just a special value of x. Okay, a is just one nice value of x. So this is our linear approximation for 4. Let me just leave here.
Sir?
Yes.
I have a question. So you wouldn't distribute it, right? The 3 over 8, you would just leave it like that. You don't have to distribute it.
You don't really have to. If you want to simplify it, you may simplify, you know.
Okay.
All right, but you don't really have to.
Okay, thank you.
You're welcome. Thank you. Or maybe I'll take your suggestion, right? Let's see. If we want to simplify this, we will get 3 over a x. Then 3 over a times negative 16. That's negative 6. Negative 6 plus a plus 2. We see exactly this is a line representation, right? A linear function. The slope is a 3 over 8, or the rate of change is a 3 over 8. All right, great. Now you try 1, 2, 3. You try those 3 questions. Okay, 1, 2, 3. Okay, so your turn to try. Let me see. Maybe I'll try. Okay, so I already have Arisa wants to try 1. Great. But do 3 of them first. Okay, try to finish 3 of them first. Then I'll have, right, then you can claim your number here. Arisa already claimed 1. Okay. All right, finish 3 of them. Emily, 3. Okay. Okay.
Professor,
Yeah.
can you make me the presenter?
Okay, but I'd like to leave 2 more minutes.
Yeah, I just wanna
Oh, okay. Let me make
download it. So
right. So who's this?
Ursa.
Ursa. Ursa. Oh, here. Oh, here. Yeah, if you want to present, get yourself ready. Let me see. Emily. Emily is already. Emily. Okay, you guys are already presenters. Yeah, it depends. Because sometimes depends. Sometimes we want to get approximation, right? We want to get exact value. So we want to maybe like the example we have square root of 3.98. We want to get decimal value for it. So it really depends. And other than that, we don't care about decimals. We like to leave exact form. We like to leave exact irrational forms. We don't want to get approximate values, but only in this case, because we really want to approximate square root of 3.98. So we would leave decimal values. Okay, let's start. So Arisa, we start with you.
Yes. So basically, first we're gonna plug -1 into the function. And as you could see, I get 4 there for f of a. And then we're going to find the derivative of the function, and we're going to get 4x to the cube plus 6x, and then plug -1 into that. And for the derivative of fa, we're going to get -10. Then we're going to use the equation L of x equals f of a plus derivative of a times x minus a, and substitute everything in, and we get 4 minus 10 times x plus 1.
Okay. All right. Yeah, if we want to simplify a little bit, like I forgot who gave the ask, we can simplify this a little bit. We see exactly this is a line representation, right? If we simplify this a little bit, Arisa, you want to simplify this a little bit?
Yes, it's going to be -10x minus 6.
That's it. Okay, you see the slope of the line. That's why it's called a linear approximation. It's a line representation. Great. All right. Thank you. Anybody has any question? Great. And so Zuli wants to show too.
Can everyone see? Hello?
Sorry. Yeah.
Oh, sorry. Okay. So we're giving the equation f of x equals sine x. And so we have a value of pi over 6. And so I chose to do the derivative of f of x, which would equal cos x. And so at a equals pi over 6, we have to find the y value, which is equal to 1/2. And then we could also find the y value of f prime, which is equal to radical 3 over 2. And so the equation would be f of a plus f prime of a times x minus a. And so that equals 1/2 plus radical 3 over 2, and then times x minus pi over 6. And then that goes out to be the equation at the bottom.
Yeah, great. That's it. That's it. Any questions? Okay, thank you. Beautiful work.
Thank you.
You're welcome. So Emily 3.
Yep, just give me a second to upload the file. Professor, I'm having trouble uploading the file. Can I just write it on the whiteboard?
Sure, go ahead.
And how do I pull that out?
You go to the arrow.
Mm-hmm.
Go to the arrow give you 3 choices. Yeah.
Yeah. Okay, so having trouble with this. Sorry for my handwriting. This is the equation. Sorry, give me 1 second. Alright, never mind. Okay, so this is the equation. Then we find f of a first. F of a being 4. Then we plug it in directly into the function, which is f of x, f of a is equal to radical 4, which gives us the answer of 2. And then we find f prime x, derivative of square root of x, which gives us the answer of 1 over 2 square root of x. Can everyone see this? I know my handwriting is pretty terrible right here. And then we find f prime a, which will equal to 1 over 2 square root of 4. And this gives us 1 over 4, which equates to the linearization of L of x is equal to 2 plus 1 over 4 parentheses x minus 4. Which simplifies further to 1/4 x plus 1.
Great. Yes, that's it. Okay. So thank you, Emily. So that's linear approximation. Anybody has any questions? Okay, so if not, we're going to chapter 3. We're going to talk about how do we use the idea of differentiation. So let me share my so applications of differentiation. Oh, actually, I leave you some work. Maybe you can try for next time. So next class. So try 11, 12, 13, 14. All right. So this is, so we approximate those values. So you need to make a function. Okay, make a function. Maybe look at this. This you can make, x raised by 4 or x minus 1 raised by 4, x plus 1 raised by 4. All right. So make your own functions. then to approximate these values. And think about the next point very close to it. And then find the differentials, right? 17 and 18. Remember what is the differential? You know, what do we call differential? Let's see, we have d dy dx. I usually call f prime. dy dx. Then the differential just the dy part. Right? So let's say dy dx equals to 1. And I can rewrite this as dy equals to 1 times dx. In this case, I just call dy, I give dy a name, differential. Right? So don't get confused with this differentiation. It's just another name. You know, usually we see dy over dx. But we can put the dx on the other side of the equation. So we call this dy differential. Right? Okay, so try those questions. So we're going to chapter 3. Talk about maximum, minimum. So we're going to talk about maximum and minimum values, right? Think about linear function. Linear function, we will never, like if the domain runs over the whole real number line, we will never have minimum value or maximum value unless we restrict it with a restricted domain. So linear function usually, you know, it goes to 2 directions. But then quadratic function, think about quadratic function. We either get an upward parabola or we get downward parabola. Upward parabola, we get this point, minimum value, right? Downward parabola, we get this point, highest point, which is the maximum value, all right? So before we know x equals to negative b over 2a, we put it in the standard form, we can find the maximum minimum. But now we have a calculus to help us, right? The minimum here, we're thinking as a minimum, as a point on the tangent line, right? The maximum here, we're thinking about the point on the tangent line. And what's the slope of a tangent line? 0, right? 0. And what's the slope of a tangent line in terms of a function? It means equals to 0. Okay, so we're going to use derivative. We're going to set the derivative at the point equals to 0 to try to find this minimum point, this maximum point. Higher polynomial functions, you know, imagine this goes on forever, this goes on forever, right? We can talk about a relative minimum and maximum. So in the interval, we say in the interval of 1 up to 7, we have this relative maximum, relative minimum. So this is the absolute minimum. This is the absolute maximum. But for this, because this function we just imagine goes on forever, it goes on forever. In the interval, we talk about a relative maximum, relative minimum. You know, we use this as a tool. You know, take function, we take the derivative of a function, then we set to 0, then we try to solve for this x. We try to find those x values. That will give us the, you know, either maximum or minimum. But by this itself, we won't be able to tell if the, you know, it will solve for x value, but it won't be able to tell the value give us maximum or minimum. But using this tool, we will find those points because the tangent line, the slope of the tangent line is 0. Okay, so we're going to do this. All right, let's see this definition. Let C be a number in the domain D of a function. Then f of C is absolute maximum, right? If the value is greater than everywhere, value everywhere, just like this. Right? We call this maximum value because f of x at this point is the biggest value than all other points. Similarly, minimum is the value less than or equal to any other y value. So this is absolute. Local maximum or local minimum are relative. It's relative to an interval, right? It's relative to a near a number. Let's see example 1. The function f of x equals cosine x takes on its local and absolute maximum and minimum, right? 1, -1. Of course, we know that. Since the cosine 2n pi, n is an integer number, 0, -1, 1, so on and so forth. So cosine of this is a minimum value. Okay, that doesn't say anything. Okay, example 2, if f of x is a quadratic function, x squared, then we have, right, we have upward parabola, we have minimum. If we have a negative x squared, we have downward parabola, we have maximum. Let's say x cubed, right? Imagine this goes on forever, this goes on forever. We do not have absolute maximum, absolute minimum. But maybe restricted. Maybe we restrict it to, we put a restricted interval. Then we can talk about minimum, maximum. Let's look at function, this function, graph of this function. So this is the 4th degree of a polynomial, because we look at the leading term, x raised by 4. That's a degree 4 polynomial. Degree 4 polynomial, and the 3 is a positive number. So that gives us an upward W-like, right? The degree 4 means the graph wiggles at the most 3 times. 1, 2, 3. So we restricted this. Of course, we do not have. If you talk about over the whole domain, we won't have maximum or minimum. But if we restrict it with a domain, so let x value run only from -1 to 4, only from -1 to 4. Then we can talk about maximum and minimum values here, right? We see we have a local maximum, local minimum. So we see this one, right? We see this one, and we see this one. At those 3 points, the derivative will be 0, because we get horizontal tangent lines. But those 2 points are not. Those 2 points are n2 points. This is n point, this is n point. Okay, this is a theorem. The theorem says if f is a continuous function on a closed interval is this, right? Closed interval means the domain includes its boundary points. So I have this equal sign. Equal sign is, with equal sign is a closed interval. A and B, A to B. Then f attains an absolute maximum value and absolute minimum value, just like this picture shows. If the function is restricted in a closed interval, here is from -1 to 4, maximum value, minimum value are guaranteed to happen. So this is, very intuitive, but it's a very, very important theorem in mathematics. You see all this, right? In a closed interval, maximum value and minimum value are guaranteed to be found. Fermat's theorem is saying if f have the local maximum, local minimum, or local minimum at C, and if the derivative at the point C exists, then f prime of C equals 0, right? Because the local maximum and local minimum has a tangent line slope to be 0. All right, slope to be 0. Okay, those x value, right, at those points. See these two. So this is C. So the value of x here is C and D. We give a name. We call those numbers, we call C and D critical numbers. And we call the point C, f of C, critical point. All right, so critical number. The critical number of a function f is a number c in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. All right, and we'll call the x value critical numbers. Okay, let's see. Let's find the critical numbers for this function. This function is defined as x raised by 3 over 5 times 4 minus x. Let's use product rule for this. So we'll take the derivative of 4 minus x, that's 4 minus x, that's negative 1 times x raised by 3 over 5. Then we'll take the derivative of x raised by 3 over 5 times 4 minus x. We simplify, we get this. Get 12 minus 8x divided by 5x raised by 2 over 5. Then we want to find critical number. So what do? We set this one equal to 0. All right, we set this one equal to 0. So we set, we get the derivative of the function. We set to be 0. Then we solve for x. So this is a rational function. The rational function to be 0, only the numerator is 0. The 12 minus 8x to be 0. Denominator can never be 0. So 12 minus 8x equals 0. We solve for x equals 3 over 2. So this function will only have one critical number. The critical number is 3 over 2. So that means at 3 over 2, we get either maximum or either minimum. So this function is drawn here, so we get maximum. So here is x value is 3 over 2. And 3 over 2, so 3 over 2 and f of 3 over 2 we call critical point. All right. So only x value we call critical number. X value with y value we call critical point. So if f has a local maximum or minimum at number c, then c is a critical number of f. So working with the closed interval method to find the absolute maximum, because remember extreme value theorem says if we're working with if the domain is a closed interval, maximum value, minimum value are guaranteed. So how to find them? This is 3 steps to find them. First, we find the values of f at critical numbers, right? So first we find the critical numbers. Then we find the value of f at those critical numbers, just like this, where we find the critical number is 3 over 2. Then we want to evaluate the function value at 3 over 2. So get f of 3 over 2, right? We can plug into the function, get the value, the y value. So the first step is getting the y value, the critical numbers. Then find the values of f at endpoints. At endpoints. Remember this picture? You see this picture? If we solve for this, we will get 3 critical points. Right? 3 critical points. And then we evaluate the function value at these 3 points. So here is given, we have 0, we have 5, we have negative 27. But then we're working with closed interval. We have to evaluate. You see the minimum and maximum? The maximum is not happening with these 3 points. The maximum happened with the endpoint. That's why we have to evaluate the endpoints. So we find the values of f function value at the endpoint of the interval. Then we compare all those values, y values. The biggest y value, right, among those will be the maximum value. The smallest value among those, the y value. When we talk about maximum, minimum, then in terms of y value, in terms of the function value. We're comparing the function value, all right? Okay, so let's see this one. Let's see example 6. So f is a degree 3 polynomial. right? Restricted, the domain is restricted with -½ and 4. So we differentiate this function. The derivative is 3x squared minus 6x, right? Then we want to solve for critical numbers. Solve for critical numbers, we set to be 0. Right? We set to be 0 right here. We set this to be 0. You know, we have 2 factors. So we solve, we get x equals 0, x equals 2. So we have 2 critical numbers for this. Then we plug in to find f of 0 and f of 2. So f of 0 is 1, f of 2 is -3. Then we have to find the endpoint, the y value at the endpoint. The endpoint is -½ and 4. So we evaluate f of -½ we get 1/8. F of 4, we get 17. So we have those 4 numbers to compare. So 17 is the biggest. So we would say this, so 4 comma 17 is the maximum point. And which one is the smallest? -3. We say 2, -3 is the minimum. We're comparing the y value, but we write down the point as a maximum point and minimum point. Okay, so let's do some exercise. Let's try to find maximum point, minimum point. Okay, let's try. So we have, we have a couple minutes. Let's try 15 up to 18. Okay, let's try this 4. I'll leave some for next class. Next class. Those are numbers, all right? 23 up to 33, those are numbers. Okay, now let's try 15, 16, 17, 18. If you finish, you can share with us. Okay, anybody like to share with us? Find the critical number. We use the to f prime of x equals to 0, right? We set f of x equals to 0, then solve for x. Of x from the equation. So this is a step, right? Oh, let me put over here. Let's see the first one. The first one is a linear function, right? So linear function, the derivative is constant. It's just a 3/2. It's a 3/2. So what does it mean? Do we have, it's constant. Can we set this one to be 0? No, it's a constant. 3/2 will be 3/2. So the first one means, right, we don't get a critical number, but we do get something else. We can evaluate, we do get, excuse me, local maximum because x is less than or equal to 3. Right? So we evaluate at x equals to 3. We would get 9 minus 1, which is a divided by 2, which is a 4. So 4 will be local maximum. Right? So we only get a local maximum for 15. 16, similarly, 16 is a linear function, right? We get f prime of x equals to -1/3. -1/3 will never be 0. So we won't get a critical number. But we evaluate at f of x equals to -2. For all x greater than or equal to -2. So what do we get? Imagine this line, right? This line is going from third to first. But then x value has to be less than or equal to 3. So add 3 down. But this one is opposite. So selective, get this. And the x value has to be greater than -2. So we have this point. So have, oops. Right? So talking about x value from this point on, from -2 point on. This one is saying from 3 down to -infinity. This is from -2 up to positive infinity. So we also get a local maximum for this at f of -2. F of -2 is, so -2 times -1/3, that's 2/3. 2/3 plus 2, that's 2, that's a over 3, right? So a over 3 will be our local maximum. Right, let's see 17. Sine x is periodic, right? But from 0 to pi/2, we do get, right, from 0 up to pi/2, we have this part of the function, sine function. And then we do get a local minimum or local maximum. But if we try, let's try to find the critical number, right? So f prime of x equals cosine x. Well, cosine x, we'll set cosine x equals 0. Cosine x equals 0, we solve x is pi/2. But here, however, we don't get a closed interval. So pi/2 is not in the domain. No, what I'm talking about. Right, yeah, pi/2 is not in the domain. But then from 0 up to a number very close to pi over 2, cosine x will never be 0. Okay? Imagine this, but then this pi over 2 is a circle. Pi over 2 is not in the domain. So here we have an empty circle at pi over 2. So we won't have a local maximum, but we do have a local minimum because at its endpoint, cosine 0, we do get a value, right, equals to 1. Sine 0. F of x equals sine 0, sine x. So f of 0 equals sine 0. Sine 0 will be 0, which is the local minimum. But we don't get local maximum because this pi over 2 is not in the domain. So we have an open circle. I won't be able to draw the open circle. Let me just get an open circle right here. Okay, let's look at this one. Let's forget about this one. All right, let's see this open circle. This open circle means C is not in the domain. So we won't be able to get a maximum value, exact maximum value. We can talk about a value very, very close to f of C, but f of C is not there. So what is a value very, very close to f of C? It's just an idea. We won't be able to get an exact value. So that's why local maximum does not exist for 17. Well, for 18, cosine t, and t is restricted from negative 3 pi over 2 up to 3 pi over 2. So we say, so negative 3 pi, where is negative 3 pi over 2? So negative measures clockwise. So negative pi over 2, negative pi, negative 3 pi over 2. Right, that's negative 3 pi over 2. Then up to 3 pi over 2, or 3 pi, so negative 3 pi over 2, up to 3 pi over 2, because 3 pi over 2 is here. So basically the domain is from here to here. So that's this domain. Okay, let's take derivative. Derivative will get a negative sign, right? Negative sine t. Well, negative sine t, then we set to be 0. Then we solve t equals to 0, right? So at this point, t equals 0. But then that will not give us critical number. Why? Because there's no, look this tangent line. What's this tangent line? It's a vertical line. The limit does not exist. So we won't be able to talk about this point. And also it's not a local minimum, local maximum anyway. So get a local maximum, local minimum on the boundary points, right? We have this f of negative 3 pi over 2. Let's hold on, the y value is 0, right? Let me see, some is undefined. Okay. Yeah. Okay, so Amir is typing in the chat. All right, so try for next class. I left some questions before in 3.1. Now I leave you some questions here to practice. All right, for next class. Okay, any questions? You know what? Maybe I choose different ones. Let's do up to 29. Then maybe you do a couple here. Okay, if no questions, I see you next Monday. All right. Okay, thank you. I'm sorry I forgot to record in the very beginning, so my recording is not whole for this time. I'm missing the first part of the class.